Well, tonight we're going to pick up some more with conic sections. I think it's pretty fun material. If I recall, last time we were talking about the ellipse, and the ellipse with center at 0, 0, and axes, foci, excuse me, at C0 and minus C0 has this standard equation. Said x squared over a squared plus y squared over b squared equals 1, where a and b are just any two numbers you want, always taken to be positive, because you can't divide by 0, right? And if they're negative, then they don't have geometrical significance. If they're positive, then they're the cine axes of the ellipse. You can figure it out by plugging in x equals or y equals 0, then you get x equals plus or minus a to satisfy that. So it goes through the point A0 minus A0. And if you plug in x equals 0, then y can only be plus or minus b. So you have this point 0b, 0 minus b. Then the foci out here at C0 and minus C0 are related to this equation by a squared, the longest distance, equals b squared plus c squared. Length, semi-major axis length, A, semi-minor axis length, B, semi meaning half of, and the focal length, distance to the foci, let's just say, C. All right, so here's the standard equation. You want to make sure you memorize that. The book puts this in a little more perspective, I guess you'd say, by also giving the equation with it translated. There gets to be too many equations to memorize. I'm going to suggest you memorize this one, and then we'll talk about how to move it around and change the orientation later. And I think it's easier to memorize how to move it and turn it than it is to memorize the more general equations. Not that it's bad to, but I think this is easier. So that'll be our standard equation for an ellipse. Now we could say something like this. Find the equation of the ellipse. We did one just sort of like this right at the end last time. With with semi-major axis length of 5 and foci at 1, 2, 1, 8. Let's see, yeah. What about that? We said that if you get the foci with the same x coordinate and different y coordinate, that actually 1 doesn't apply anymore. This is for the ellipse with the foci in the x-axis, or in the x direction at least, centered at 0. What about this one? Here's what we do. is the foci are vertical, right? You've got the same x coordinate. And centered at the point halfway between, right? Average 8 and 2 and you get 5, right? 8 plus 2 over 2, averaging was 5. So they're centered at the point 1, 5. So this must be the center of the ellipse. Just from the drawing over here, you observe that the center is always halfway between the foci. And so what kind of equation do we look for this time in order to make the foci up and down instead of left and right, and centered at 1, 5 instead of at 0, 0, right? This was the center here, 0, 0. Maybe I should label this center, focus, focus. And these other 4 points are sometimes called vertices. Term not used a lot, but we'll write it out. Okay. Trying to keep the noise down from the next room there. Okay, so what we really seek is this. One, to make the foci vertical centered at 0, we rewrite this as x squared over b squared plus y squared over a squared equals 1. The idea is in this thing, and I should have written it down by now even, is A has to be bigger than B. If A equals B, if you think about it, this is an equation for a circle at the origin because it's x squared plus y squared equals a squared. A circle of radius A, if you put A equal B. So it degenerates to a circle. So one of these has to be bigger. By convention, we say A is the bigger number, and if A is under X, then that puts the foci in this direction. So now if we switch it and put A under Y, now with the larger number, again, A bigger than B, the larger number under Y, you just realize that all this is the first equation, essentially with X and Y interchanged, right? We put Y over A and X over B, and otherwise it's the same equation. If X and Y are interchanged, then it's the same ellipse turned this way. So now the foci are at 0C, 0 minus C, because all we did was interchange X and Y in that equation. And 0A, 0 minus A are the vertices at the end of the major axis. And here B0, minus B0, and B0 are the vertices at the end of the semi-minor axis. And it'll still be centered at 0, 0 since that one was, right? And so now we're getting an equation like that. Well, that's not quite good enough still. That puts the foci vertical like we wanted, right? So the difference in the y coordinates it gives the foci rather difference in the x coordinates. We also want to move the center of those. The center is 0, 0, 2, 1, 5. How do we do that? Here's an important property. In any equation whatsoever, it doesn't matter if it's a function or whatever, whatever graph it has, if you replace x by x minus x naught and y by y minus y naught, it moves the graph rigidly like it's a fixed wire. Take this thing and just slide it over in exactly the same shape and puts the center wherever you want at x naught, y naught. So if we replace this by this equation, x by x minus x naught, and y by y minus y naught, this will move it. X naught, whatever you subtract horizontally, and y naught, whatever you subtract vertically. It works like this. I just want to give you this little side note here. You say, why is it what you subtracted? If you subtract 2, then it moves it plus 2 in x. Why is that? Here's just a typical example I like to give. If you take the parabola, y equals x squared, and you want to move it over, right? It goes through these points, minus 1, 1, 0, 0, and 1, 1. Suppose I want to move it over 2 units to the right. What's the equation of the parabola now? when the vertex here is at 2, 0. What I can do in this equation, let's move it 2 over and 1 up. So that the vertex is at 2, 1. What I do is I replace x by x minus 2, so it moves 2 horizontally, and y by y minus 1 in the equation. Just wherever I see y, I put parentheses. Wherever I see x, I put parentheses. And I put, instead of x, x minus 2, instead of y, y minus 1. And if you think about it now, whatever satisfied, whatever x, y satisfied this one, if I make y 1 unit greater and x 2 units greater, then this one will have the same number on the left as this one, and this one will have the same number squared on the right as the other one. The equation will still be satisfied because I'll get the same numbers on the left and right as I did here. If I just make y1 greater and x2 greater. It follows then that every point is the same, just x is 2 larger here and y is 1 greater, so it will satisfy the equation the same way. So that means the 0, 0 moves to 2, 1 because I changed 2 and x and 2, 1 and y. This one becomes add 2 and add 1, I get 3, 2. And this one becomes add 2 to x squared, I get 1, add 1 to this one, I get 2, so I get 1, 2. And so it's exactly the same shape. And you can do that with any graph in the plane whatsoever. Just replace x by x minus a number, or y by y minus a number, whatever you subtract from each is the shift. So that's what I'll do to this one. If I want to move it so the vertex is at 1, 5, evidently this is x naught and this is y naught for the shift in this equation. This is the equation I'm going to want here. This problem. Right, because now the foci are vertical, going to put a under the y, and this will encompass the shift, the x naught and y naught. So now what I have is the focal length. I can find c from the foci that I have. C is half the distance between the two foci, right? But it's 6 units between foci. This from the original picture is 1/2 the distance between. So C must be equal to 3. The semi-major axis length is 5. A equals 5 was given. So now we can calculate B by this equation. B, if A squared equals B squared plus C squared, solving for B, we get B equals square root A squared minus C squared plus B square root of 5 squared minus 3 squared is in fact 4. So B is going to be 4, A is going to be 5, x naught, y naught are 1, 5. I've got it, right? I've got all the numbers in equation 2. And then I can also find the foci from that one. We'll say by equation 2, desired ellipse has equation, or let's say is x minus 1 x shift squared over semi-minor axis length squared 4 squared plus y minus the y shift squared over semi-major axis length squared, which is 5 squared, all equals 1. There's its equation. So it's not too hard to figure these out. Got to think about it, but a little practice makes you very good at this quickly. That's about as hard as they get, ellipses. And then there's some similar things we do with the rest of the conic sections. So the next one then, the hyperbola. We're not going to do much with circles. I assume you've already done a fair amount of that in algebra, but we will run into them once in a while. You should recall those. A hyperbola have standard equation. We talked about its properties last time. X squared over a squared minus y squared over b squared equals 1. Here we did not assume that a is necessarily bigger than b. In fact, it can be equal and it doesn't degenerate also. So a and b are any positive numbers now. Whatsoever. They do have geometrical significance again. We mentioned before geometry of this thing, that the hyperbola is the set of all points, such that the difference of the two distances from two given numbers, two given points called the foci, is a given constant. So it has that property, and it has those optical properties we mentioned. But how can we deduce equations? This is what it comes out when you write that property, that the sum of the two, the difference of the two distances from the 2 points is a given constant. It comes out to be this equation. And so this is the one you have to memorize. So memorize the one equation for the ellipse, memorize this one equation for the hyperbola. And the rest you can figure out in exactly the same way. If you need to turn it the other direction, then you just interchange x and y. Usually, however, when we turn these, we still keep b under y. We'll mention that in 1 minute. And then if you need to translate, you just replace x by x minus x naught, y by y minus y naught. It's just like that. You just memorize one basic equation for each conic section, and then after that, you just turn it by interchanging x and y, and then you translate it by replacing the variables. All right, so let's mention that one. And here is the picture for the hyperbola. We'll just give you this when it's in standard position. The way you get this again is you start with your foci at C0 and minus C0. And then it turns out that when you have this equation, the foci are always at C0 minus C0, in which A, B, and C are related again, but this time it's different. It looks like a Pythagorean theorem. It's C squared equals A squared plus B squared, because this time the focal distance is big as C. So you need to memorize that one too. It's different. In the ellipse, it's A squared equals B squared plus C squared. For the hyperbola, it's C squared equals A squared plus B squared. Relates to 3 important numbers. The 2 that are in the equation, and C, the focal length, that you can derive from the equation by this. All right, and so the foci are there, and the hyperbola looks something like this. It actually approaches asymptotes. We're not going to try and prove this. It takes too much time and get away from calculus. It's not too hard, but although technically the asymptotes are a calculus concept. Oops, I brought it through C0. Do that. I happens when I'm talking right sometimes at the same time. There we go. Okay, so it looks like that. And you look at the equation and figure out that if you put y equals 0, x must be plus or minus a to make this equation full, right? So this is actually the point A0. We call that a vertex of the hyperbola. And this one must be minus A0, another vertex of the hyperbola. Furthermore, C0 and minus C0 are called the foci, plural of focus, of this hyperbola. It looks like that. And where does B come in? Kind of interesting. Where's B in this one? Well, it turns out, if you think about it, here's a calculus concept. If you solve this one for y as a function of x and take the limit, what you'll see is that as x goes to infinity, y goes closer and closer to plus or minus b over ax. So this asymptote has equation y equals b over ax, and this asymptote has equation y equals minus b over ax. That's the limit of the quotient y over x is b over a. If you write this out, take the limit. So there's how the hyperbola comes out when you write that standard equation there. Centered at the origin, foci on the x-axis at plus or minus c, just like the ellipse, has the same equation except one thing. That's what makes this easy to memorize. You just change the plus from an ellipse to a minus. Now it's a hyperbola. And then technically, A and B doesn't have to have A greater than B anymore. All right, there's what it looks like. And then we can note that for foci at 0C and 0 minus C on the y-axis instead, that's still centered at 0, right? 0, 0 is halfway between these 2 points. We similarly get y squared over b squared minus x squared over a squared. Convention is to leave the b under the y. You effectively just interchange x and y in that equation, but you also bother to interchange a and b for this one. It's more convenient. The reason is that if you do it this way, the foci are still plus or minus y equals plus or minus b over ax. So same asymptote equations. You solve for y here and take the limit. You see you get the ratio b over a. And now, when x equals 0, you get y equals plus or minus b. So you go through this point here, 0b minus b. And now we're going to approach the asymptotes this way. So there's what the hyperbola looks like if you interchange x and y and also a and b for convenience. It looks like that, opening up and down instead of left and right. Okay, and then we say A, B, and C are related by the same equation down there. C squared equals A squared plus B squared. Now we can do a nice similar problem with the hyperbola. And so there's 2 things you want to be able to do. You want to be able to make a sketch from the equation, and then you want to be able to find an equation from the properties or sketch. So suppose I did this one. Suppose the first bunch of problems on the homework is just to sketch some of these. What if I asked you to sketch x minus 1 squared over 2 squared minus y plus 1 squared over 3 squared equals 1. Can I sketch that? Sure I can. It's very easy, actually. How do I do it? Look at the you look at the equation here. If the x term is first, it's a positive 1 here. Right, first you notice it's a hyperbola because it's of this form, x squared over a squared minus y squared over b squared equals 1 instead of plus for the ellipse. So it opens left and right. We know it's going to do that. If you now use the equation you can find c by the equation down here. It's the square root of a squared plus b squared. Pythagorean theorem. Well, that's the square root of 2 squared plus 3 squared is the square root of 13. So these foci on the x-axis are going to be a plus or minus square root 13. You want we label a point. Now, what about the other ones? We know in this case that we plug in y equals 0 and get plus or minus a for these. So if this is a here that's squared, evidently this intersects at plus or minus 2. So minus 2, 0. plus 2, 0 is where the vertices are. And then finally, we need to draw the asymptotes. So asymptotes, once we really calculate these for the test, y equals plus or minus b over ax, right? There's two of them. That's y equals plus or minus, let's see, b was 3 and a was 2. B is allowed to be bigger than a in this problem. Plus or minus 3 over 2x. So it's a line, two lines through the origin. These for the standard equation, I always go through the origin. And with slope 3/2, right? Because this, after all, is y equals mx plus b. Right, so the y-intercept is 0. They go through the origin. The slope is plus or minus 3/2, depending on which line you pick. So we make it kind of steep like this, right? Steeper in slope 1, splitting the axes. Make it a little bit like that. And now I just have to draw the hyperbola so that each branch, these pieces are called branches, approaches the asymptote. So we draw it like that. There's one branch. There's the other branch. Pretty good picture of a hyperbola. How about that? So now only one more thing remains, right? This was for the hyperbola x squared over 2 squared plus y squared over 3 squared equals 1 when I set it at the origin, but I've also translated here whenever, so this is the equation here, x squared over 2 squared minus y squared over 3 squared equals 1. How do I get from this, right? Well, I just have to move it, right? Replacing x by x minus x naught, y by y minus y naught translates it. X naught in the x direction, y naught in the y direction. Let's see where it goes. The center, instead of being 0, 0, is now at what's subtracted, 1 minus 1. So the center is going to be right there. And everything moves with it. What are the new equations for the asymptotes? Asymptotes translate similarly. You just put y equals y plus 1 equals plus or minus 3/2 x minus 1. So you just translate the asymptotes by the same translations. There's the new asymptotes, and they will look exactly the same, just shifted over. So there's slope 3/2 just intersecting at this point instead of at the origin. Now what you do is the vertices still have to be 2 units to the left and right. So if this is 1 minus 1, then I go over here, the 3 minus 1, 2 units to the right, and I go 2 units to the left, minus 1, minus 1, and those are the vertices. And I just draw the same picture I had right over there. I just shifted it down 1 and right 1. Should look just like that one. Uh-oh. Assuming you can draw it too. It looks about like that, approaching the asymptotes on the end. So here's a sketch of this one. For a general hyperbola, what you do is just memorize this first picture here that went with this. And then if you interchange x and y so that y is the positive term, then the hyperbola will open up and down. You memorize this asymptote equations also. Let's see, where to put those. You want to memorize these asymptote equations. Let's put a box. Y equals plus or minus b over ax for the hyperbola at the origin will be the asymptotes. And so you need those 3 equations for dealing with hyperbolas. Any questions on all that? Does that look all right? Well, I want you to be able to sketch ellipses. I want you to be able to find an equation for ellipse from being given some of its properties. I want you to be able to sketch hyperbolas. Let's see if we can find an equation for a hyperbola from some of its properties. How about this one? Find the hyperbola, that is its equation. with vertices, well, 0, 12, 0, minus 12, 0, 13, 0, minus 13, and then 0, 12 and 0, minus 12, and foci. 0, 13, 0, minus 13. How about that? Suppose I gave you the vertices and the foci, for instance. That's enough actually to determine a unique hyperbola. I think it's nice to picture these things in your mind at this point. And what you do first, I think this always helps me to do it first, to say, where's the center? Once I know the center, that'll get in my way. The center has to be halfway between the vertices or halfway between the foci. So you can do either one. Halfway between both is the point 0, 0, right? And you can do it this way, 0 and average the two y coordinates. Find the center, you can average the two x coordinates and the two y coordinates. And you get the point 0, 0. But this one you can just look at and see, right? All right, so the center is at 0, 0. That's nice. That means we don't have to translate this one, right? Now the foci, the vertices are vertical. As are the foci. That says I need to put the y term first, right? Which said if it's supposed to open up and down, I guess I erased it. Then you write y squared over b squared minus x squared over a squared 1 with the y term positive. That's for vertical vertices at the origin. So we're set. Now, if we also had the center somewhere else, we'd have to replace these with x minus x naught, y minus y naught. So there's that. And now, if I have these, I know immediately what A and C are, right? This one says half the distance between the vertices is A, so A must be equal to 12, right? I said A, but these are vertically. This is B. This is B, the number of their halfway between the vertices when it opens left and right is A. Halfway between the vertices when it opens up and down is B. So this number B will be 12. And then similarly here, halfway between the foci, half the distance between the foci is C, right? C is half the distance between the foci. And now if I know B and C, I immediately know A. All right, since C squared equals A squared plus B squared, Pythagorean theorem. You can solve that for A and say that A is the square root C squared minus B squared. Well, that's the square root of 13 squared minus 12 squared. So if you work it out, it's 25 square root. So A is 5. Now I've got it, right? Once I've got A, B, and C, I can plot everything, right? I have to know the center. So it's centered at 0, 0. And the foci are at 0, 13, 0, 0 minus 13. And I can get the asymptotes and the equation. We said for vertical foci, you've got y squared over b squared minus x squared over a squared equals 1 becomes y squared over 12 squared minus x squared over a is 5. 5 squared equals 1 is the equation. There it is. Now with the hyperbole, you also want to know the asymptotes. So the asymptotes are y equals, in either case, opening vertically or horizontally, plus or minus b over ax becomes y equals plus or minus 12/5 x are the asymptotes. There's finding the hyperbola equation from the properties or from the graph. If I would have drawn this graph, we could have done it too. Well, there's one more note on these hyperbolas we need to do also. Sometimes it's hard to sketch this very well. And if you put this little help in here, it makes it a little more accurate. This is what pretty much every textbook does. So note on sketching asymptotes. If I have, let's do the standard case, x squared over a squared minus y squared over b squared equals 1. We recall that this goes through plus or minus a, 0. And it approaches the asymptotes, y equals plus or minus b over ax. Well, this distance here is 2a, right? A to hit to the middle and then a to the other side. I could make a box that's 2a by 2b. Yes. Let's make this one 2b long. I'll go b units up from the center and b units down, a units right of the center and b units left, a units left. And now what I observe is this is b, this is a. The slope of this line is b over a. This is precisely the asymptote going through the corner of the box. So if you draw a 2a by 2b box centered at the middle of the hyperbola, asymptotes will go right through the corner. That's a nice way to draw the asymptotes, is to draw this box and put them through the corners. So on this one here, we could do that and say if we wanted to sketch that, we would put the vertices through plus or minus 12. And the asymptotes, we slope 12/5, so it's a little bit bigger than slope 2, a little more negative than slope minus 2. So we're looking at something like that. And you can go over to this point here, 5 this way, 12 this way. Asymptotes go right through the corners there. It looks like I didn't get this one right. So there's the asymptotes going through the corners of the box. Well, that's what I want you to be able to do with hyperbolas. Find the equation or draw the sketch, those two things. Now some important notes come up. Why would these things be so important? One is we see those great applications, but even more than that, it helps us with some basic algebra problems, right? What is every equation ax plus by plus c equals 0 represent? Remember? This is actually the general form of an equation for a line if you assume a and b are not both 0. At least one of them is not zero. This is the line. And it's the general form. All lines can be put in that form. All equations that form are line. What is the next most difficult equation you can think of in algebra with two variables, x and y? Similarly, so these are lines. Similarly, suppose we go up 1 degree and put ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Where a through f are numbers, and suppose that maybe a, b, and c aren't all 0. Then you get a conic section in general. We'll say similarly, this equation with arbitrary letters here is either a conic section. Remember the conic sections? There's just parabolas, ellipses, hyperbolas, and circles. Or it could be a degenerate case, like we could intersect the cone and get a couple of intersecting lines, or we could get a line, or we could get a point. Or the last thing is it might have no solution, right? If I put f equals 1 and all these other letters equal to 0, then I get 1 equals 0 and there's no solution, right? So those are the three cases. This is really marvelous, right? Because now we know how to sketch any equation with second degree. We can have an x, y, so that the two powers add up to 2. We can have x squared and y squared. But these polynomials and two variables, very important in algebra, of second degree, always come out to be a conic section, a degenerate case, or no solution, depending on the value of the letter. We're not in a position to prove that easily, so I'll just say that's the case. Shortly, we'll be in a position where with a lot of work, we could prove it, but I think it's not worth it. So we'll just point out, here's the equation for a line. First degree polynomial equals 0. Put a second degree polynomial on two variables equal to 0. You get a conic section, a degenerate case, or no solution. All right, well, we have one more conic section to do also. Was the parabola. They have this nice property we said is a set of all points that are equidistant from a line, and another point called the focus, just to remind you, you have this kind of a thing. If suppose I put the vertex of the parabola at 0, 0. And suppose I put the focal point here at 0p. Instead of 0c, we'll call it 0p this time. And then the so-called directrix must be the line y equals minus p. If 0p is the focus and 0, 0 is the vertex. Why? Because, right, every point of the parabola, such as this one, has to be equidistant from the focus, well, it's p units up to the focus, and the directrix. So the directrix must be p units down, since the focus is p units up. So that's why this follows immediately from those points. And now, what is the standard equation for a parabola like that with vertex at the origin and opening up? With focus at 0p, p greater than 0. the equation turns out to be very simple, and it's kind of complicated to derive it, so I'll leave it out. But it's 4p that's x, let's write it this way, x squared equals 4py. So there's the equation, that one. You can see immediately that 0, 0 is a solution, for instance, but this generates all the other. Now, if you want if p is less than 0, then it opens downward. And if you interchange x and y, you can switch the direction. So you can turn this any direction and open it the opposite direction just by those kind of things. So we'll say note for downward, you memorize this equation, and p equals the focal length. For downward, if you assume p is positive, then it's x squared equals minus 4py, or you just allow p to be negative. For opening right, you just interchange x and y in that equation. You get y squared equals 4px. And for a parabola opening left, you just put minus in here, and you get y squared equals minus 4x. Y squared equals minus 4px. So these are all the alternative equations, but I don't say memorize those. I won't start on them. I'm just saying figure out that if you interchange x and y in the equation, like this, that makes it open right instead of up. And if you put a minus in here, then it turns it upside down, right? Y is now minus in here what it was in here. Solve for y. There's how to sketch parabolas. They're relatively easy compared to the other ones we've been doing, I think. And so suppose we said this one, sketch y minus 1 square, y minus 1 equals 8 x plus 2 squared. That's immediately a parabola. All right, I can rewrite this equivalently as 1/8 y minus 1. Let's switch sides. X plus 2 squared equals 1/8 y minus 1. And what have I got? I've got this equation here, right? Except translated. So this is evidently by that equation. This is a parabola. Except instead of having vertex at 0, 0, we now have vertex at whatever subtracted here, minus 2, 1. X minus 2, 1, according to the shift. Since it's of this form, it's opening upward. We didn't have to change variables or put a minus in there. And then p, what is p? Well, this is supposed to be 4p. So 4p equals 1/8. P must be 1/32. That's the focal length, right? So here's what it looks like then. Opens upward, has this focus at 0, 1/32. Oops, except it's got to be translated. Let's do this one first. And opening upward. Oops. Vertex at the origin for now. So This would be the parabola y equals 8x squared at steeper, I suppose. So if its focus is right there, then it's pretty steep. And now we translate, we replace y by y minus 1, x by x minus a negative 2. And so it moves 1 in y and negative 2 in x. Vertex is now, instead of being at 0, 0, now it's negative 2, 1. That's the shift. And the focus should be 1/32 of a unit above there. So the minus 2, 33 30-seconds would be the focus. And I just write exactly the same shape. It was just move 2 units left and 1 unit up. Here's y minus 1 equals 8x plus 2 squared. What's harder on the parabolas, of course, is finding the equation from the information, but it's not too bad. We just do the same thing again. Find the parabola, that is its equation, with vertex 1, 1 and focal length 1, opening to the right. Well, if it opens to the right, we interchange x and y in this equation, and we write y squared equals 4px. Right. Now it'll open to the right. But now we also want to put the vertex at 1, 1, so we replace y by y minus 1 and x by x minus 1. That translates it. There's the equation for the parabola. Opening right, vertex at 1, 1. All I need to find is p. Well, I know the focal length is 1, so I just put that in. So I rewrite now y minus 1 squared equals 4 times x minus 1. Okay, so there's finding an equation for a parabola, giving some of its. Some of them they might give you the directrix of the focus. We should do one of those. It's a little trickier. That's the easy example. Find the parabola with directrix y equals 3 and focus 0, 1. How about that? I think it almost helps to sketch this and try and visualize it and figure out the letters from that. So if I put the focus at 0, 1 and the directrix at y equals 3, what do I immediately know when I picture that in my mind or draw it on the board? I know from memory that the vertex goes halfway between the focus and the director, right? So this must be immediately the vertex at 0, 2. So the parabola is going to go through there. I know since the directrix is above the focus, it opens down. Focus is below directrix. Once I know it opens down, I can write its equation immediately, right? The equation for a parabola going down with vertex at the origin It would be x squared equals 4 dy minus, right? So it goes down instead of up. But I've shifted it. The vertex is at 0, 2. So I need to replace y by y minus 2. This is a downward parabola. I had to put the minus in the original equation, I gotta go down. And replace y by y minus 2 makes it with vertex at 0, 2. Now all I have to do is find p, right? Well, what's p? You can look at the diagram again. It's either the distance from the vertex to the focus or from the vertex to the directrix. In either case, you can observe the p. So evidently x squared equals minus 4 y minus 2. There is the equation for my parabola that I want. Well, try a bunch of those problems. Here's my list. I think I'll make you good at these. As you can see, these have lots of applications, and they're also an important algebraic case. Out of 10.4 on conic sections, we'll get 3 to 25 odd. Now, the next section carries us even further as it picks up right where this one left off. We can start a little bit on that tonight. I don't think I'll assign homework on it yet. The big question is now, well, we've moved the conic sections around in the plane and we've turned them opening left and right or up or down. What if it's a tilted one? What if it's rotated in the plane? That's the next section. This section is actually really important because for people in engineering and that kind of thing, not only do you rotate conic sections, you rotate other things in exactly the same way we're going to introduce here. This really makes more sense if you take linear algebra first, because you can derive this over a long period of time. We don't have time to derive it here, so we'll just say rotating conic sections is the same linear algebra trick and this is how it works. Substituting x equals x prime times cosine theta minus y prime times sine theta, and y equals x prime sine theta plus y prime cosine theta. Again, it takes too long to derive that for this class. I'll leave that for linear algebra. But this turns out where theta is a given constant, theta turns out to be an angle. If you plot what this looks like, think about it. This is x equals a number times x prime plus a number times y prime, and these primes are not derivatives. They are a new notation. I prefer to put hat or something like that so you don't think it's a derivative. This yields the x prime, y prime coordinate plane. This is the change of coordinates. We're replacing x and y in the equation with these expressions where theta is a given constant. So you now have the equation in terms of x prime and y prime instead of x and y. And you can look in the xy coordinate system. And because these are linear equations, I won't leave this unmotivated, even though I won't prove it. Because these are linear equations, they take lines to lines. And actually, the way this one is set up, it keeps perpendicular lines perpendicular, it turns out. Particular one. And so what it does is it gives you a new coordinate frame, a new set of rectangular coordinates and they turn out to just be rotated by an angle theta. So with the x prime, y prime axes rotated by theta in the xy plane. So here's what the picture looks like. Just for a little motivation. Suppose you took the line y equals 0, the x-axis, sorry, x prime equals y prime equals 0, the y prime system. Then this would fall out, and you just get x prime cosine theta, x prime sine theta. You get a line that looks like this through the origin. Put that straight in the middle. So let's put it like that. Here's the x prime axis compared to the x-axis, and it's rotated the angle theta, whatever number you put in there. And the y prime axis rotated the same. It's now theta, angle theta, counterclockwise like that. And what you have is a new coordinate system with the same origin, just rotated. That's how you can rotate coordinate systems. It's nothing more than taking your equation in x and y and making this substitution. You might ask, well, if we got it in the x prime, y prime system, maybe we can rotate it back. How would we rotate it back? Well, we have to rotate it by an angle minus theta. We want to rotate by minus theta. We just put minus theta in here, and then the minus comes out of the sign because it's an odd function, makes this plus. Minus comes out of here and makes this minus. So you, for that reason, to rotate back, or to inverse these and get back x, y by a substitution. You just use the following reverse coordinate transformation. X prime on the left and y prime on the left now are now x cosine theta plus y sine theta. Y prime is minus x sine theta plus y cosine. So these are the equations to substitute back in the new equations to recover your original equation. You have to memorize these. You should memorize these, although they're not as important. I'll put a star on there, but you can get by without this. And so if you have parabola that's rotated, it has a not so nice equation in xy coordinates, it turns out. But if you switch to rotated coordinates, where the axes go like that, now it has an easy equation. And so you can take one of those equations that we said are all parabolas and ellipses and hyperbolas, etc. And if we just rotate our coordinates, we can see one of these standard forms. So now, by these, let's call this equation 1. By the substitution 1, any conic section, which we can recall can always be written in the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0 for some constants a through f. Every conic section can be written in that form. And everything in this form is either a conic section, a degenerate case, or no solution. But any conic section, we can write it in that form. If you do this, any conic section of that form, upon completing the square, also, we'll do an example of what we mean by that, can be put into one of the standard forms for a conic section, whereby you can recognize how to graph it. So this can be put in standard form with a shift. Translation, we'll call it. So there's the trick for this section. The trick is now just to figure out what angle is going to make it so that the axes are oriented right. This one is a hard proof. We'll just say it turns out that to do this, to make it so that it can go into standard form, because the axes are tilted just right, so the rectrix is down here and the focus is up here kind of thing. It turns out that what you want is cotangent of 2 theta equals a minus c over b. This one is too hard to derive. I hate to say it, but you just have to memorize this. I don't want to give you too much to memorize, but it's not too hard. There's the equation for finding theta, such that those rotations will put this into standard form. Well, we can only do one example today, but we'll do nice examples next time. That's why I'm not giving you the homework on this one. Just finish the homework on conic sections. Try those and bring questions next time. I really wish you'd bring more questions, actually, at the beginning. As fast as I need it. Here's a nice, easy example to illustrate this. We'll take a real simple equation of this form and see that it actually comes out to be a conic section. Here's one you've probably seen in algebra before. Suppose I asked you to identify the conic section, degenerate case, or no solution. X, Y equals 4. And sketch it. This is a very confusing question, because if you would have come in before this class, you'd probably figure out how to do it. Now that I've given you all this stuff, maybe it's harder. But once you see this, you'll appreciate how to do harder cases, so that this will come back. What is this? You notice this is what you would have thought of before from algebra. This is equivalently y equals 4 over x. Maybe you recognize from algebra that's actually a hyperbola. Remember how to sketch these? It just looks like this and like this. There's the 2 branches. This is how you're used to seeing common hyperbolas done, is this kind of thing. This is just the standard equation we did there before, rotated. Let's find out that this actually is true, what you sort of intuitively knew from algebra. Identify x, y equals 4 and sketch. This is actually the form star here, right? This is star with, well, there's no x squared term, so a equals 0. There is an xy term, b equals 1. You know, I better do this. I wrote capital letters here. I wrote small ones here. My apologies. In the book, they used capitals, so I'll just use capitals too. A, B, C, D, E, F. Sorry about that. But you want to make a statement down there. So this is star with capital A equals 0, capital B equals 1, C equals 0, since there's no y squared term, there's no x term, so D equals 0, no y term, so E equals 0, but F is over on the other side. F equals, if you bring this over to -4, you observe that F equals -4. So this is that equation right there, with only 2 of the numbers not 0, right? Nonetheless, this comes out to be a conic section. How do we rotate? To rotate into a standard form, waste my time here. We use these equations here. I'm going to call them double star. First, you take by star and find the angle. Sorry about that. Triple star. Should have numbered these before. By triple star, the rotation equation, cotangent of 2 theta must be a minus c. Well, a and c are 0. Over b is 1. So the cotangent has to be equal to 0. Right? You can actually choose any theta whatsoever that makes the cotangent equal to 0. Sometimes it's easier to solve that by using tangent. But since it's 0, I don't want to say one over. But the cotangent, maybe you remember, looks like this. There's an asymptote. I should draw this on solid. It goes through this equation, or through this point, pi over 2, and it has intercepts of the x-axis at odd multiples of pi over 2, and asymptotes at multiples of pi. So here's x equals pi, and here's x equals 0. There's y equals cotangent c, cotangent x. So if I think of this as x, what I want is x equals pi over 2, right? So 2 theta equals pi over 2 out of the cotangent graph. Cotangent is 0 and cotangent x is 0 and x is pi over 2, so I want 2 theta equals pi over 2. This is equivalent to saying theta equals pi over 4. That's the rotation angle. Again, if you pick 3 pi over 4, that would work also. Then divide it by 2, you just have to take 3 pi over 2 here. You get 3 pi over 4, would also rotate in a standard position. It would just interchange the direction and points in the x prime, y prime plane. So this one works. Now what I do is I write my equations. X equals x prime cosine of this is 1 over square root 2 minus y prime sine of this is 1 over square root 2. And then y has to be replaced in the equation by x prime sine 45 degrees plus y prime cosine 45 degrees. And these substitutions make the equation xy equals 4 into the equivalent equation x prime over square root 2 minus y prime over square root 2 times, that's x, and then y is x prime over square root 2 plus y prime over square root 2 equals 1. And this actually, with some work, comes out then to be x prime squared, right? Just FOIL it out. X prime squared over 2 minus y prime squared over 2 equals 1. There's our standard equation. It says if you rotate this 45 degrees so that x prime is here, it's the standard equation with opening about the x-axis with vertex 2 units out, square root 2 units out. It looks like that, and there you've got it. We can do asymptotes and that sort of thing next time, but it's just our standard form rotated 45 degrees, just as we expected. Try the homework and we'll pick up on this next time. Hope you enjoy the talk. I think it's kind of fun.